Lens Lab will give you a chance to observe the formation of images by a single converging lens, and also to test the predictions of the thin lens equation. Before we begin, we need to agree on a sign convention. Most physics books use what we call the empirical sign convention, which has the distance from the object to the lens, the object distance, as a positive quantity. And when a real projected image forms, the distance from the lens to that image is also a positive quantity. In all the photon and photon-2 materials, we prefer to use the Cartesian convention. First of all, this is the same convention that everyone learns in math class. The lens is 0, the optical axis is 0, and everything to the left of the lens is negative, and everything to the right of the lens is positive, whether it's an object or an image. This convention also simplifies problems where there are multiple lenses and images are being formed that are intermediate images. If you're using the Cartesian sign convention, then it's very important that you use this form of the thin lens equation. We also like this form of the thin lens equation because it's very simple to remember. Light starts at the object at a distance d sub o, object distance from the lens. It then passes through the lens of focal length f and creates, equals, an image, which is located at an image distance d sub I. So light goes from the object through the lens to form an image. This is a classic lab, and I encourage you, before you jump into taking measurements, to first play around with the lens a little bit. For example, use the lens to form an image of an object that is infinitely far away, or at least at a large distance. Here's an image of the world outside my window. You can see that the colors are preserved and that the image is inverted. The sky's at the bottom and the parking lot is at the top. You also notice there's some distortion or blurriness around the edges. This is a very short focal length lens, and there's quite a bit of aberration. In order to take the measurements, it's first important to be sure that the object, the lens, and the screen are all at the same height and along the same row of holes. We have the object mounted on a tilt table, post and post holder. We have the lens mounted squarely in a bar-type lens holder, post and post holder. And the screen, which is an index card, is simply taped to a bar-type lens holder. I have these on bases because the object of this lab is to measure the object distance and the image distance for a number of different object distances. And it's just much easier to do if you can slide both the lens and the screen back and forth. So we begin by setting the object distance to a certain amount as specified in the lab, and then we slide the screen back and forth until we find the image. The object distance is measured with a meter stick from object to lens. The image distance, again, measured from lens to image. A couple of questions that you might pose. One is, what happens if you put the lens very close to the object? What happens to the image? What happens if the lens is exactly one focal length away? What happens if the object distance is very, very large, as when I was using the world outside as my object? And finally, what happens if you cover a portion of the lens? Say cover the top half of the lens, or cover the side of the lens, or maybe cover, put a ring around the lens so that only the center portion is used. What do you think will happen to the image?